Welcome to Musical Chemistry. This is an interactive audiovisual instrument that transforms the periodic table of elements into music using vintage synthesizer emulation. Every one of the 118 chemical elements produces a distinct tone. Atomic properties like mass, ionization energy, and electronegativity determine the sound characteristics. Let's start by clicking on individual elements. First, hydrogen, the lightest element. Listen to the sound and let it sustain. Now helium, a noble gas. Notice how it sounds completely different from hydrogen. Helium uses additive synthesis with multiple harmonics. Lithium is an alkali metal. Alkali metals use the Tb3O3 acid-base synthesizer, giving them a squelchy, resonant character. Listen to that characteristic filter sweep. Let's examine carbon more closely. First, we'll click carbon to hear it, then open the info panel to see all its properties. Here we see carbon, atomic number 6, atomic mass 12.01, and it's a nonmetal. The electron shell visualization shows carbon's 6 electrons orbiting the nucleus. The synthesizer display shows this uses the Yamaha DX7 for FM synthesis. Carbon, as a nonmetal, uses the Yamaha DX7, the legendary frequency modulation synthesizer from the 1980s. Different element categories use different synthesis engines. Musical chemistry uses 9 vintage synthesizer emulations. Let's explore several different element categories and their synthesis techniques. Sodium is an alkali metal. Listen to its squelchy, resonant acid-base sound from the legendary Tb3O3. That's the classic acid house sound with resonant filter sweeps. The synthesizer display shows the Tb3O3 using a sawtooth oscillator through a resonant low-pass filter with envelope modulation. This creates that signature acid-base character. Now let's try a noble gas. Argon uses the Synclavier, which builds sounds from up to 16 sine wave harmonics. Notice how bright and bell-like it sounds. The Synclavier builds this sound from multiple sine wave partials, each with its own envelope. Higher harmonics decay faster, creating a natural, bell-like quality. Iron is a transition metal. It uses the PPG wave, which morphs between different waveforms over time. Listen as the timbre evolves from smooth to aggressive. The PPG wave crossfades between sine, triangle, sawtooth, and square waves, creating constantly evolving timbres. This was revolutionary technology in the 1980s. Now let's explore chemical compounds. When you click a compound, all of its constituent elements play simultaneously as a chord. Let's switch to the compounds browser. Let's click on water, H2O. This contains 2 hydrogen atoms and 1 oxygen atom, creating a 3-note chord. Listen to how the elements blend together harmonically. Now carbon dioxide, CO2. 1 carbon and 2 oxygen atoms. Notice how the chord has a completely different character from water, even though it also has 3 notes. The carbon uses FM synthesis while oxygen uses FM as well, creating rich harmonic interactions. Ammonia, NH3. 1 nitrogen and 3 hydrogen atoms, creating a 4-note chord. Nitrogen and hydrogen both use the DX7, creating a cohesive FM synthesis timbre. The same compound can sound very different depending on how its notes are arranged across the frequency spectrum. This is called voicing. Let's explore the 5 voicing modes using water. Close voicing keeps all elements in the same octave, creating a tight, compact sound. Listen to how dense and clustered this sounds. Open voicing alternates between octaves, creating more space and separation. Same compound, completely different spatial character. Notice how much wider and more open it sounds. Wide voicing spreads the notes across 3 octaves, creating maximum spaciousness and clarity. This is perfect for complex chords with many elements, preventing harmonic mud. Mass-based voicing is unique to musical chemistry. Light elements like hydrogen go high, heavy elements go low. Hydrogen has a mass of 1, so it plays 2 octaves up. Oxygen has a mass of 16, so it plays in the bass octave. This creates voicings based on actual atomic mass. Let's explore more complex compounds. Organic molecules contain many carbon, hydrogen, and oxygen atoms, creating rich, layered chords. Let's switch to the organic compounds category. Glucose, C6H12O6. That's 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms, all playing together as a massive 24-note chord. Listen to how rich and complex this sounds with wide voicing. The wide voicing spreads all 24 notes across 3 octaves. Each element finds its own space in the frequency spectrum, creating a lush pad-like texture without muddiness. Now let's create a musical progression. The progression player lets you sequence up to 8 chords that play one after another, creating evolving harmonic landscapes. We'll add 4 compounds: water, carbon dioxide, ammonia, and methane. Watch the progression slots fill as each compound is added. Now let's press play. Each chord will play for 2 seconds before moving to the next. The progression loops continuously, creating an evolving 4-chord sequence. Listen as the progression loops. Each compound creates a different harmonic color, and together they form a musical journey through chemistry. You can modify the tempo, change voicing, or add more compounds at any time. Now let's explore the arpeggiator. The arpeggiator works with the progression player. Instead of playing all notes simultaneously, it plays them one at a time in various patterns, transforming chords into melodies. First, let's configure the arpeggiator settings. The up mode sorts notes by frequency from lowest to highest. We'll add water to the progression 4 times and play it with the arpeggiator enabled. Notice how the 3 notes play in sequence, low to high, rather than together. Down mode reverses the sequence, playing from highest to lowest. This creates a descending melodic line from the same 3 notes. Random mode shuffles the notes, creating unpredictable, generative sequences. Each time you play, the order changes. Let's try this with ammonia's 4 notes. Musical chemistry has unique arpeggiator modes based on actual chemistry. Atomic order sequences notes by atomic number. For ammonia, hydrogen comes first with atomic number 1, then nitrogen at 7. Mass order sorts by atomic mass, from lightest to heaviest. Let's hear glucose's 24 notes sequenced by mass. Hydrogen is lightest at mass 1, then carbon at 12, then oxygen at 16. Orbital mode is the most chemically sophisticated. It follows the Aufbau principle, the order in which electron orbitals fill according to quantum mechanics. 1s, 2s, 2p, and so on. Listen as glucose's 24 notes sequence by quantum orbital order. You've now explored musical chemistry. 118 elements, 9 vintage synthesizers, 5 voicing modes, 9 arpeggiator patterns, and infinite sonic possibilities. Click elements, create compounds, build progressions, experiment with voicings and arpeggiators. Every element, every compound, is a musical instrument waiting to be played. Enjoy your journey through the sonic periodic table.